So today we're going to talk about the limit of a function and infinity. So basically 2.3, depending on the book you use, is kind of a long section. So it might even be 2.3 and 2.4 if you're using the Briggs book, or if you're using the Stewart book, it'll just be 2.3, but it'll be 2 videos. It's a long section. So the first part that we're going to talk about, if you want to think about it as like 2.3 part 1, is the limit of a function and infinity. So we say that we have, in all the previous problems we did in the previous section, it was always a finite number, or the limit didn't exist, or something like that was occurring. So for in this section, we're going to deal with when the limit is equal to infinity or negative infinity. Now, in some circumstances, you don't actually want the limit to be infinity or negative infinity, but it's kind of we kind of agree that we're allowed to say that that limit is infinity or negative infinity, rather than saying it does not exist. It just depends on the context you're using it in. So in general, we are allowed to say that a limit approaches infinity, as long as it's approaching the same version of infinity, positive or negative, from both sides. So if we say that the limit as x approaches 0 of 1 over x squared, we want to know what this equals, right? So what we're going to do is we're going to kind of fall back on our method of, plugging numbers to the left of 0 in and plugging numbers to the right of 0. Now, again, we can't plug 0 in, even though it's a rational function, because we can't divide by 0. So what we're going to do is what you see I did over here and over here is I made 2 tables to the left of 0 and to the right of 0. So I used x equals 0.1, 0.01, and 0.001. These are just arbitrary. You could pick any one that you want, but normally you try to pick numbers that get closer and closer to the value of a, in this case 0. And then when I plug 0.1 in, I get 100. When I plug 0.01 in, I get 10,000. And when I plug in 0.001 in, I get 1 million. Remember, you're squaring 0.001. And if you think about it, you're taking 1 and you're dividing it by 0.001 squared, which is basically 0.00001, right? So we end up with 1 million. So as we can see, this side over here is getting larger and larger as this side over here is getting closer and closer to 0. Okay, now we're going to use the same thinking over here. This side, once again, is getting larger and larger, and this side is getting closer and closer to 0, but from the left-hand side. And remember, because it's squaring it, it turns out that from the left and from the right, we're approaching a height of infinity. So we're going to say that this is, in fact, infinity. And if you think about it, if you look at it graphically, you guys remember that if you look at this graphically, this would be the graph, something like this, right? And you can see that from the left side of 0 or from the right side of 0, my height is, I'm skyrocketing, I'm approaching infinity. So this is something that, we're going to now have to deal with, is that we are able to get infinity as our limit. Remember, limits, you don't actually get to make it, you get to get so close, and you get to approach them and become arbitrarily close or infinitely close, but you don't actually say you made it. And well, that's perfect. That goes perfect with infinity, because we don't actually make it to infinity either, right? Infinity is the idea of the biggest thing there is, the biggest number there is. So in general, we say that the limit as x approaches a of f of x is equal to plus or minus infinity, means we get arbitrarily large plus or minus output by taking x values closer and closer to x equals a. The limit as x approaches a of f of x equals infinity. Remember, if and only if the limit as x approaches a from the right equals infinity, and x approaches a from the left of f of x is equal to infinity, the limit. So as long as you get the same version of infinity, both positive or both negative, you're allowed to say that that limit is infinity. And you do similar for negative infinity right here, okay? So now let's try this one. So you guys should pause the video now and try to use a little table here and plug in values. I chose to use 1.9, 1.99, and I'm getting closer and closer to 2 on the left, like this is our left side, and this is our right side, right, of 2. So I'm getting closer and closer to the left and to the right of 2, all right? So then what we're gonna do is, let me see here. So I'd like you to pause the video and give this one a shot. Sorry, my internet is looking a little bit rough. So I'm hoping it'll get a little bit better. Okay, so hopefully you guys are back from the video and you should be able to plug in 1.9, 1.99. Okay, so I'm going to take this and I'm going to plug this in my calculator. I'm going to do 4 divided by 1.9. Oops, I'm going to use parentheses. 1.9 minus 2. And I get negative 40. Oops. Negative 40. Now I'm going to do 4 divided by 1.99 minus 2. And I'm going to get negative 400. And then I'm going to do 4 divided by negative 1.99. Oops, I'm sorry. That's wrong. 1.999 minus 2. And I'm going to get 4,000 negative. Now I'm going to do the same thing over on the other side. I'm going to do 4 divided by 2.01, 2.1 minus 2. And we get 40. And then this one will be 400, and then this one will be 4,000. This one is approaching negative infinity. This one is approaching positive infinity, it looks like. So this has an answer of D and E. Because remember, the limit as x approaches 2 from the left of 4 over x minus 2, that one looks like from the left side, we're getting close to negative infinity. And the limit as x approaches 2 from the right of 4 over x minus 2, it appears that we're approaching positive infinity. And remember, these two values must be the same in order to say that the true limit or the pure limit exists, okay? So in this case, we get D and E. And that happens. It's, you know, that this is a rational function. You know, it's going to be one of those graphs that does, something, let's see. From the left side of 2, it's approaching negative infinity, so it's probably going like this, right? And from the right side of 2, it looks like it's approaching positive infinity, so it's probably going like that. And then right here will be the asymptote probably, okay? So you can kind of see that graphically the graph backs up what our tables are telling us, okay? So let's look at a little bit of a follow-up. So it says determine the value of the infinite limit, the limit as x approaches 3 from the right of x plus 1 over x minus 3 quantity squared. Use reasoning to explain your answer. Okay, I'm going to pause the recording real quick just to fix my internet. Okay, so hopefully no more hiccups, guys. So I'm back, and I'd like you guys to pause the video, but this time I'd like you to try to explain, like thinking about numbers and small numbers and large numbers and dividing by small numbers or dividing by large numbers, and think about a way that we could explain using reasoning what we think the limit is, what we think the infinite limit of limit as x approaches 3 from the right of x plus 1 over x minus 3 squared. Okay. All right, so hopefully you guys are back. So we have to use some kind of reasoning. So what I'd like to do is let's talk about as x gets closer and closer to 3 from the right. So as x approaches 3 from the right, we think of values like 3.01 or 3.00001 or something along those lines, right? Okay. When you subtract three from these numbers close to 3, the result is a very small positive number, right? So we're going to get a very, very small positive number, right? The numerator, and when we say small positive, we mean like 0.000000001, right? Because remember, whatever you get when you subtract, you're then going to square it. So it's going to be even smaller than it was before. And you're talking about a very small number already, a very small decimal. When you square a small decimal, it just becomes a smaller decimal. So we're talking about our denominator has a very small decimal. The numerator is approaching 4 as x approaches 3 from the right. Right? Because you have 3.01, 3.00001, and then you're going to add 1 to that. So you're going to be thinking about getting close to 4 in your numerator. So a constant, let me see how I can say this. Since our numerator is approaching a value of 4 and our denominator is approaching a value, a very, let's say very, very small number. Since our numerator is approaching a value of 4 and our denominator is approaching a very, very small number, we say the limit is approaching. So let's see, let's take 4 and divide it by 0.00001. You're going to get some massive positive number. So we say that it is approaching positive infinity, okay? So then that means I could come over here and say the limit as x approaches 3 from the right of this is approaching positive infinity. Okay, so again, we didn't do tables, and you might think that tables are actually easier, but sometimes it's nice to be able to explain yourself and kind of tell people what your mind is thinking. So I often, if we were in class together, I would talk to you about, I'd always over exaggerate like 0.00001. I'd say, what if you had like, 3.001 and you had enough zeros all the way to wrap around the earth and to the sun? That still is not infinitely close. That's still measurable, right? So we're getting even closer than that to 3. So then your denominator is just becoming smaller and smaller and smaller. It's approaching 0, okay, in your denominator. So when you have a constant divided by a number that is very, very small or infinitely small, you say that the outcome would be infinity or negative infinity, depending. So here's just kind of a follow-up of that. It says, if the numerator is tending to a constant that is not 0 or plus or minus infinity, and the denominator is tending to a number positive or negative that is very close to 0, then the limit will be infinite. You need to then determine if it is positive or negative infinity, okay? So if your numerator is tending to a constant, like we were in this problem, we were tending to 4, right? Let me see. Yeah, we were tending to 4. And not 0. Obviously, 0 is not the constant we're talking about. It's tending to a constant that is not 0 or plus or minus infinity. And the denominator is tending to a number that is positive or negative, that is very close to 0, so 0.00001, positive or negative, then the limit will be infinite, okay? So this kind of leads into the next idea. A vertical asymptote is a vertical line that graphs oops, I think I wrote a typo here. A vertical line is a vertical asymptote is a vertical line that a graph, oh no, it gets arbitrarily close to, but never crosses. When one or more of the following are true, there will be a vertical asymptote at x equals a. The limit as x approaches a from the right of f of x is equal to plus or minus infinity. The limit as x approaches a from the left of f of x equals plus or minus infinity. And the limit as x approaches a of f of x equals plus or minus infinity. So if any of these take place, you have a vertical asymptote at x equals a. So for our course, you guys are not allowed to say, oh, it's division by zero, so it's a vertical asymptote. That's in pre-calc, you're allowed to say that, not in calculus. You have to normally show why there's a vertical asymptote, whether it's tables, reasoning, quick explanation. But in general, I expect to see some kind of reasoning behind why you have a vertical asymptote. You can't just say like, oh, f of x equals 2 over x plus 3. Oh, we're going to have a vertical asymptote at x equals -3. And you can't just say that. You have to then go on to say, well, the limit from the left or the limit from the right or the limit is equal to plus infinity or minus infinity or whatever. You have to show me these limits to show me that the vertical asymptote exists there, okay? All right, let's see. Okay, so that's the vertical asymptote. So let's try one of these, okay? So let's try to find a vertical asymptote. So it says use limits to determine where f of x equals x over x minus 2 cubed has a vertical asymptote. Okay. And then, once you find the vertical asymptote, tell me where they are. So the part about pre-calculus is you can say, okay, well, we know where to look for the vertical asymptote. We know to look for the vertical asymptote at x equals 2, right? So we know to look for the vertical asymptote at x equals 2. Now we just have to prove there is one there. So this is where pre-calculus comes in, and it tells you, oh, if you plug 2 in there, you get division by 0. So something's going on there. So now we have to determine if it's a vertical asymptote. So I'm just going to do the limit as x approaches 2 from the right of x over x minus 2 quantity cubed, okay? So we can use, I guess we could use a table if you want. So I'm going to go from the right of 2. So here's x, and here's f of x. Okay. I'll do 3. We might need more, but we'll see how it goes. Okay. So I'm going to take, I guess we'll go 2.01, 2.001, and we'll go 2.0001. That should be good. So I'm going to take out my calculator. I'm going to do 2.01 divided by parentheses 2.01 minus 2 cubed. Okay, so let me make sure. So I get a massive number. I get I think it's 2 million. Yeah. Okay, so let me try this again. Let's do 2.001 divided by parentheses 2.001 minus 2 to the power of 3. Yeah, so I get a massive number again. 3, 6, 1, 2, 3, 4, 5, 6. I think this will actually be good enough. We don't even need to go. That's already at 2 billion, right? So, and then, that's going to be even bigger. It's going to be to blah, some really big number. So we can see from this that the limit as x approaches 2 from the right of x over x minus 2 quantity cubed is approaching infinity, right? It's getting larger and larger and larger very quickly. So that means if we look up here, a vertical asymptote occurs whenever any of these happen. If I get from the right infinity or negative infinity, if I get from the left infinity or negative infinity, or I get from the true limit of negative infinity. So if any of these happen, we have a vertical asymptote, or if more than one happens, we have vertical asymptote. So we know we have a vertical asymptote at x equals 2. So that would be your answer. This is kind of like your work. This is your verification or your conclusion, I guess. And then you now know you have a vertical asymptote at x equals 2. Okay? And that's all there is to it to determine a vertical asymptote. Sometimes it's harder, sometimes it's easier. But in general, it's all about knowing where to look. And then once you look, you then take a limit from the left to the right of the value. If you're dealing with exponentials like e to the x's and natural logs of x's and stuff, sometimes I would check, well, natural logs are kind of weird, but I would check both sides. If from either side you get plus or minus infinity, you're done, right? The moment you get plus or minus infinity, you know there's a vertical asymptote somewhere. So normally that's how we go. Okay, is we check from the left or the right. I tend to always try to check from the positive side, whatever makes it positive, just so I don't have to deal with the negatives. But you know, sometimes it doesn't work out that way. Okay, you guys, I think that's going to do it for part 1 of this video, and then we'll have another follow-up one for 2.3, where we'll get into more of the limit laws and using them to find limits. It's a much more difficult section. It actually requires a lot more algebra and everything like that. But that'll do it for this video. Thanks for watching, guys.